A drone looks simple: a camera, a battery, a propeller, a radio link, sometimes a warhead because engineers occasionally wake up and choose violence. That is the visible machine. The real system is much larger. A modern drone often depends on satellites before it ever leaves the ground. Satellites help it navigate. Satellites help operators communicate with it. Satellites help planners find targets. Satellites help forecast weather. Satellites help armies synchronize the wider fight. So the strategic question is simple. Why do drones need satellites to fight? The answer is that drones are not isolated weapons. They are extensions of a larger network. The drone is the claw. Orbit is part of the nervous system. Start with navigation. A drone has to know where it is. For many systems, that means satellite navigation. The American GPS constellation is the most famous example. But China uses Beidou, Russia uses GLONASS, and Europe uses Galileo. These signals help drones fly routes, hold position, return home, and strike targets. That sounds ordinary until the signal is jammed. In Ukraine, GPS jamming has become a constant feature of the battlefield. Russian electronic warfare has disrupted drones, precision weapons, and navigation systems. A drone does not have to be shot down to be defeated. It can be confused. A confused drone is a tiny aircraft having a theological crisis. If it loses navigation, it may miss the target, drift away, crash, or return to the wrong location. That means satellite navigation is a strength and a vulnerability. It gives drones precision, but it also gives the enemy something to attack. This is why serious militaries are investing in backup navigation. Inertial systems, terrain matching, visual navigation, better antennas, anti-jam signals, and autonomy all matter. The goal is not to abandon satellites. The goal is to keep fighting when the enemy attacks the satellite link. That brings us to communications. Small drones often use direct radio links. The operator is nearby. The drone flies over a trench, a field, or a road. The range is limited. Larger drones need more reach. If a drone is flying hundreds or thousands of miles away, line-of-sight control is not enough. It needs beyond line-of-sight communications. Satellite communications make that possible. SATCOM lets operators send commands, receive video, update missions, and connect drones to a wider command network. This matters for long-range surveillance drones, maritime drones, and systems operating in deserts, oceans, mountains, or remote islands. Ukraine, again, gives the clearest public example. Starlink helped Ukrainian forces maintain battlefield communications after Russia disrupted other systems. That did not make Starlink magic. It made it useful infrastructure. There is a difference. Magic belongs in fairy tales. Infrastructure belongs in budget fights. A satellite link gives drones reach. It also creates dependence. A country may buy thousands of drones, but if it cannot protect the communications layer, those drones become local tools rather than theater-wide assets. They may still be useful, but they cannot operate as part of a larger machine. This is especially important in the Pacific. A drone in Europe may operate near dense roads, towers, fiber networks, and friendly bases. A drone over the Pacific may be operating across water, far from infrastructure, in a theater where distance is the enemy's unpaid assistant. In that environment, satellite communications are not a luxury. They are part of the fight. The third reason drones need satellites is intelligence. Before a drone launches, someone has to know where to send it. Satellite imagery helps locate targets, track ships, map roads, observe troop movements, identify air defenses, and monitor changes over time. Optical satellites can show visible details. Radar satellites can see through clouds and darkness. Radio frequency sensing can detect certain emissions. Drones are often called intelligence platforms, and they are. But drones also consume intelligence. A drone sent to the wrong grid square is a flying apology. The pattern usually works like this. Satellites watch the broad area. Drones inspect the local target. Artillery, missiles, aircraft, or other drones conduct the strike. Then, satellites and drones help assess what happened. This is the modern kill chain. See, decide, strike, assess, repeat. The faster that loop becomes, the more dangerous the force becomes. That is why satellites and drones are natural partners. Satellites provide wide area awareness. Drones provide close inspection and local action. One gives the map, the other walks the ground, except with propellers and less dignity. The fourth reason is weather. This sounds dull, which means it is probably important. Drones are sensitive to wind, rain, icing, heat, cold, dust, and clouds. Batteries lose performance in extreme temperatures. Optical sensors struggle with clouds and smoke. Small drones can be pushed off course by wind. Maritime drones care about sea state. Larger drones still need weather planning for launch, flight, sensor use, and recovery. Weather satellites help planners decide when drones can fly and what sensors they can use. No one makes heroic posters about military weather forecasting, but war has always been ruled by conditions. Mud stopped armies, storms sank fleets, clouds hide targets, wind bullies small aircraft with the enthusiasm of a schoolyard tyrant. A drone force that ignores weather will donate equipment to the landscape. The fifth reason is timing. GPS is not only about location. It also provides precise timing. Military networks use timing to synchronize communications, coordinate operations, support data links, and keep systems working together. When timing is degraded, the effects can spread across the network. This matters because drones rarely fight alone. They may be connected to artillery units, command posts, intelligence cells, aircraft, ships, or other drones. If the timing layer becomes unreliable, coordination gets harder. Modern war runs on synchronization. Without it, units still fight, but the larger system slows down. A force can become a crowd of brave people with expensive equipment and poor rhythm. History contains many such crowds. They usually get footnotes, not statues. Now we get to the real issue, vulnerability. If drones depend on satellites, then enemies will attack the connection. They can jam GPS. They can spoof navigation signals. They can disrupt satellite communications. They can hack ground systems. They can attack user terminals. They can target ground stations. In extreme cases, they can threaten satellites directly. Counterspace warfare does not always look like an explosion in orbit. Often, it looks like a frozen video feed, a missing signal, a navigation error, a drone that fails to return, a mission that takes too long because the network is degraded. That is why the drone war is also an electronic war. The cheap aircraft gets attention because it produces dramatic footage. The spectrum fight is less visible, but it decides whether the drone can talk, navigate, and act. This is the part most people miss. Drones do not remove the need for advanced militaries. They increase the importance of networks, satellites, operators, software, replacement capacity, and electronic warfare. A cheap drone can destroy an expensive vehicle. True, but a serious drone force is not cheap once you count the training pipeline, batteries, launchers, terminals, data links, mapping, satellite access, software updates, electronic protection, and replacement stock. The drone may be cheap, the system is not. This is why industrial capacity matters. Drones are attritable. Many will be lost. The side that can replace them, adapt them, and connect them to a resilient network gains power. That means production lines matter, spare parts matter, software teams matter, satellite bandwidth matters, launch capacity matters, ground stations matter, cybersecurity matters. War has a cruel way of making boring things majestic. A nation that wants to dominate with drones must also protect the space architecture behind them. It needs satellite navigation that can resist jamming. It needs alternate communications paths. It needs drones that can keep operating when links degrade. It needs commanders trained for partial blindness. Because in a major war, the enemy will not politely leave the network alone. The lesson is clear. Drones changed modern war because they made reconnaissance and strike cheaper, faster, and more widely available. But they did not escape the old rule of military power. Every weapon depends on a system. For drones, That system runs through orbit. Satellites give drones position, reach, intelligence, timing, and weather awareness. They help turn small flying machines into parts of a larger battlefield network. When that space layer works, drones become scouts, spotters, strikers, relays, and decoys. When it fails, they become shorter ranged, blinder, and more local. Some will still fight. The best forces will train for that. The worst will learn it after the signal disappears. So the next time you see drone footage from a battlefield, do not only look at the aircraft, look above it. Look at the navigation satellites. Look at the communications links. Look at the imagery that found the target. Look at the weather data that shaped the mission. Look at the jammers trying to tear the chain apart. The drone is the part you can see. The war is being fought through the system behind it. And increasingly, that system runs through space.